So our second speaker is Ranveer Kumar Singh. So he completed his integrated master with a major in mathematics from IISER Bhopal and is currently a PhD student at New High Energy Theory Center working under Gregory Moore at Rajkot. And the title of his talk is Generalization of Monster Denominator Identity to Higher Level using Harmonic Math.
Thank you for the introduction. Let me start by thanking the organizers for the opportunity to give a talk here. So let me start with the monster denominator identity that we are trying to generalize. So I will use both z and tau in upper half plane. And as was already introduced by Professor Murthy in his talk, the j function is this ratio, where E4 is the Eisenstein series. So Ek is the Eisenstein series. Q is, as usual, e to the 2 pi iz. And delta is the Ramanujan's discriminant function, which is this. So this j function satisfies this amazing infinite product identity. So here P is e to the 2 pi I tau. And Cmn are Fourier coefficients of Jz minus 744. So I'll explain why this. So this 744 has been subtracted so that this function doesn't have a constant term. And then these coefficients appear in the exponent here. Now, this is related to the denominator identity for the monster Lie algebra. So this is and monster Lie algebra is basically an infinite dimensional Lie algebra, which appears when we are trying to prove the monstrous Moonshine conjecture. Now, our goal is to generalize this formula to higher levels. So goal is to, let me say, so by higher level, we mean that, so here J is a modular function for SL2Z. So it is invariant under the action of SL2Z. What we want to do is we want a similar formula, but for modular functions for gamma naught n, for example. So so the first task is to construct such functions which are invariant under gamma naught n, and that's where harmonic mass forms would be useful. So so the I'll explain these two indices here. Oh, okay. So let me first explain why we need a whole system of functions here. So it turns out that this denominator identity is equivalent to another identity called the Asai Kaneko Ninomi identity. So this identity is as follows. So if we consider this sum, then this is equal to this identity can be used to prove the monster denominator formula. And here, what are these functions that are appearing? So Jm tau is basically equals to J1 applied, Hecke operator applied on J1. And J1 is simply, I think this starts from 0. J1 is J minus 744, and J0 is just 1. And we can use this formula to prove the monster denominator identity. I'll explain a proof at the end of the talk in the general setting. So what we first want to construct are the generalizations of these JMs, which satisfy this kind of an identity. So we'll construct all these functions and then show that when we apply some kind of Hecke operator on Jn1, then it gives us Jnm. And then we will use a generalization of this kind of an identity to prove a similar infinite product formula. So let me begin with the construction. So before that, maybe I can write down the general formula. So this is what we will prove. So J, N, M, Z, these are harmonic mass forms of weight 0 for gamma naught n. So these have an expansion of this form. So here Z is x plus Iy. And I'll write down the expression for these coefficients later. Right now, let us just assume that these J and M's have this kind of an expansion. Now, then what we can prove is the following. Under certain assumptions that I'll explain when I state the theorem, under certain assumptions on n and these functions, one can prove this. Sorry? Oh, these. So I'll construct these functions. So I said that we want to construct a family of modular functions for gamma naught n. Right now, I'm just assuming that I have such functions and I have this expansion. I'll construct it in a moment. Then I can prove that we have the following infinite product expansion. And here, So these numbers are given in terms of Fourier coefficients of this function. Now, let me now start by constructing these functions. So oh yeah, I think the R is here in this exponential. Let me confirm if there is an R. Oh yeah. Sorry, yeah. So this is what we have. So this J appears on the right hand side. Oh, okay, okay. Let me write this. Is this visible? Yeah, okay. So yeah, sorry about that. So R appears here in the denominator here. This is GCD of R and then. So I'm sorry, yeah, I think, sorry, yeah. Yes, so it will be, so later I'll assume that these are holomorphic and that will put some constraints on capital N and yeah, that will put constraints on capital N. Then this is not true. This is true under some assumptions that I'll explain later. So for example, we have to assume that N is square free. Jn1 and Jn over and these conditions can be satisfied for certain values of N. There is an infinite class of capital N's for which these are satisfied. And for those N's, this identity is true. Yeah, so that is something we are still trying to figure out. Right now, we have not found a representation theoretic connection of this formula. So we don't know whether this comes from some Lie algebra or not. Yeah, yeah. So here, this formula is coming from monster Lie algebra, but there we don't know if it is coming from a Lie algebra. So I don't think it is directly related to the monster Lie group, but it may be that there is some other infinite dimensional Lie algebra whose denominator identity is that infinite product. But yeah, we don't know right now.
Our CMA coefficients, but there is no negative.
Yeah, yeah. So those will be zero. So only. Yeah, yeah. So here n must be, so n negative one is allowed because you have a, yes, only that one is allowed. Other than that, all of them are zero. Yeah. Yes, yes. Yeah, so I guess we can say that this is -1 to infinity. So to construct these JMs, we use this non-holomorphic Poincare series. So these functions are defined by this coset sum. So gamma infinity is basically the stabilizer group of the cusp infinity. And IS, this is the Bessel function. And this series converges in the region real is greater than 1. So now first one has to, so once we prove that the series converges absolutely in this region, then we can show that this is invariant under gamma naught n, because the cosets just rearrange among themselves. Now we can try to figure out the analytic continuation. And one can do that. So what we can do is write down the Fourier expansion for the series. And in the Fourier coefficients, we need to take s going to 1. And this has been done earlier. So there is a result by Hazel from 2011, I think, where the analytic continuation for this function has been figured out. And then we can define this limit. And it turns out that, so we can also show that this is invariant under the action of, so this is annihilated by delta 0 if we take s equals 1. So the general result is that the action of delta 0 on f and m is s times s minus 1 of. So once we take s going to 0 limit, this becomes this is the function is annihilated by delta 0, and then this is a harmonic mass form. So this has an expansion. So before that, we can define this function to be so this b plus n m0 is just the constant term in the Fourier expansion of this function. So we have just removed the constant term. So these, now we have constructed this family of functions which are harmonic mass forms of weight 0. Now the next goal is to show that there is a Hecke operator under which these Jn functions satisfy the following relation. So we want to show that the following relation holds. So here, if we just take the standard Hecke operator, then this is not true. This is true only for n equals 1 when the GCD of, so if we take the standard normalized Hecke operator, then this is true only when m and capital N are co-prime. But if we want to generalize this to all m, then we have to generalize the Hecke operator here. And so we need to use equivariant Hecke operators. So this result is from 2017 by Brinkman, Kane, Lobrick, Ono, and Roland for co-prime m and n. So we are trying to generalize that using equivariant Hecke operators. Now, if I get time at the end, then I'll explain what is equivariance here. For now, let me just define it. So equivariant Hecke operator acting on J and M is defined like this. So we have the usual sum So the only difference is that we have changed the number here. So we have divided by a and n. And because of this, now we can show that the following holds. Now, to prove this, all we need to do is substitute this definition in the Fourier expansion. So we have an exact Fourier expansion for these JNMs. Let me actually write it down. Yeah. This equation? So I will show towards the end that using this identity, it's a few lines of algebra. But to actually prove it using Lie algebra is pretty hard because we have to construct this monster Lie algebra. And that was done by Borcherds in 1992, I suppose. So that proof is difficult, but using that identity, it's pretty easy. Yeah. So proving that identity. Yeah, this identity, I'm not sure how difficult it is to prove. Yeah, so there is another way that equation can be proved. So there is this formula for divisors of modular forms. Using that, one can also prove that. It turns out that that formula, which I'll write down in a while, that is equivalent to that formula. And that formula is again equivalent to the monster Lie algebra. So there are three different statements which are equivalent. And yeah, I think the first one is easiest to prove. So let me write it down. Oh, okay. So I already wrote down this Fourier expansion here. Let me just write down the expression for these things. It's not very difficult. So this is for n greater than 0. And there is a similar expression for n less than 0 with modulus here inside the square root. K is the Kloosterman sum, yes. Let me. For n less than 0, we have the other Bessel function appearing here. And the constant term probably I don't need to write because we have already subtracted it off. K is the Kloosterman sum. Right, so with this explicit expression for the Fourier coefficients, proving this is not very difficult. It's a few lines of algebra. We need to use some properties of the Kloosterman sum. There are some identities that we need to use. And just replacing this Fourier expansion on the right-hand side gives this relation. Okay, so now let me come to the divisor formula which we use to prove this identity. So I think it's 2006. I'm not sure about this, but given any meromorphic modular form, this is for level 1. The following identity holds. So by meromorphic modular forms, all I mean is that we now allow poles in the upper half plane as well. Okay, so this operator was denoted by D earlier. But the notation for this operator is theta in this context. So I'll write it down. So here, it's tau of Z is just this sum. And theta is just this operator, which is same as, this was denoted by D in the previous talk. And E tau is basically this 1 over E tau is the stabilizer subgroup of tau. Modulo plus minus identity. And order tau f is the order of the pole or 0 of the function at tau. Now, this formula was proven by Bruinier, Ono, and I forgot the Conan, right? Thanks. So yeah, so this formula was proved for any meromorphic modular form. Now, using this formula, one can prove the infinite product identity that I wrote earlier. So, and this the proof of this formula is complex analytic. So we can simply use complex analysis to prove this formula. So I think if we go this way, if we prove this formula first and then go to the infinite product identity, that's easier rather than going through representation theory. But the representation theory proof actually generalizes to a huge class of infinite product formulas. So the idea now is to generalize this formula to higher level and then use it to prove this the infinite product formula that I wrote earlier. And such a generalization is already available. Let me write it down. So for gamma naught n, if we take a meromorphic function of weight k for gamma naught n, let me assume n square free, and I'll explain why. So then the following is true. And here Hn tau is basically this sum. E and tau as before is the order of the stabilizer group, but in gamma naught n now. Yeah. So the reason I assumed n square free is that if n is not square free, then there are other contributions here. And we don't want those contributions to prove the infinite product formula. If there are other contributions, then we don't have an infinite product formula. So now the idea is to apply this formula to Jn function that we just constructed. If we do that, then we can see that okay, I erased that formula. But what we want is something like this. So we want to compute this. This will give us this term. And because the weight is 0, this term is not there. So all I will have is this. Oh. Okay, I forgot to say that Fn here is the fundamental domain for gamma naught n. So we'll have something like this. Let me just write f for this function. And this is very similar to the BKO identity, which can be used to prove the monster denominator formula. So the idea is to use this formula and prove the infinite product identity that I wrote. So first we need to compute this. So one can just apply this operator on the Fourier expansion that I had written earlier. And there is a explicit formula for the action of this operator, can be found in the book. And once we use that, we find that this is simply the Poincare series of weight 2. So in fact, something more general is true. So P is the Poincare series of weight 2, and it has an expansion of this form. I think there is a minus sign. These coefficients B and M can again be written in this form with some change in the prefactor here. But it has a similar expression. So we have also found a generalization of the BKO identity in this case, which was not known earlier. So let me write down that identity. It will be useful later. Okay. So we have the following. So this index 2 here is simply the weight of the Poincare series. me just write F. So this is the generalization of the AKN identity. Now we want to use this to prove the infinite product formula. So are there any questions before this, before we do that? Right. So one way to define it is exactly the same way we constructed these functions using analytic continuation. When we define it using analytic continuation, we can exactly compute its Fourier expansion. And we will find that you get the same Fourier expansion as you get by applying theta on these functions here. So this can be proved in both ways. These two things can be constructed independently, and then you can apply this theta operator and get this relation. So one thing I should mention here is that here we are using the fact that Jn1 is holomorphic. Or meromorphic, in fact. So because this formula holds only for meromorphic modular forms, so this must be at least complex analytic. And Jns that we have here, these Jns, these are harmonic mass forms, so they are just smooth, they are not analytic. So we need to assume that these functions are holomorphic on H for this identity to hold. And that's why when we'll prove the infinite product identity, this assumption is also useful there. So, okay. So what we want to do is integrate this equation. So we can integrate this equation both sides with respect to Q. So what we get is the following. So left-hand side, theta is simply Q d over dq. So what I can do is write and I have removed the power of Q here, which I will pull it out and send it to the right-hand side. So right-hand side, I will have this equation. Is it visible here? This is what I have. So the Q from left-hand side, when I take it to the right-hand side, it just becomes n minus 1 here. Now, what I want to do is simplify this sum. And for that, I will use the valence formula. So so as a function from H to C, using the expression that I wrote in terms of the Bessel function, what one can show is that this function has a pole only at I infinity, and it is holomorphic at every other cusp. So as and of course, I have assumed that this is holomorphic on H. So it has a pole at I infinity, and so now once we have this, then we can consider this function as functions between these compact Riemann surfaces. So x naught n is basically the compact Riemann surface associated to the fundamental domain of gamma naught n. But now I need to include the cusps. Once I include the cusps, then x naught n becomes a compact Riemann surface. On the right hand side, this is just C union I infinity. So now this is also compact. Topologically, this is a sphere. So now this function is holomorphic as a functions between Riemann surfaces. And then I can use standard results from Riemann surface theory that says that one result which I'll use is that number of poles equals number of zeros. And when I apply this to F, which was then this tells me that F has only a simple 0 at z equals tau. So so now I can use this in the formula. So here the sum now becomes a sum only over I infinity. So what I get is the following. This sum, maybe it's better because tau is appearing here. No, I think this is fine. Here, so this sum now has only two contributions. One from tau prime equals right. So one from z equals tau and the other from z equals I infinity. Okay. So this order tau prime just means the order of the zero or pole of this function at z equals tau prime, right? So this sum has only two contributions, from one from z equals tau and the other from z equals I infinity. And so this becomes so this one comes from I infinity because at I infinity the function has a simple pole. Sorry, this would be -1. And E n tau prime at I infinity is just 1. And now the valence formula tells me that this whole sum has to be equal to 0. So This is the formula. This is the valence formula. This is valence formula only for weight 0 modular forms. So once I apply that, I just get that En tau this equals 1. And now I can just plug it in here in this sum on the right hand side. The sum has only one term, because if n does not contain I infinity. So if n here does not contain I infinity. Let me leave this here. Okay, so once I do that, this whole sum becomes just one term. And now all I have is this whole thing is gone. This sum is just 1. And all I have is this. Okay, and now I will just integrate both the sides. So then that gives me the following. Left hand side, I just get log. There was a minus sign here because here there is a minus sign. So that minus sign is still there. So I get log this equals so I need to treat n equals 0 term separately because that's 1 over q. That will give me log q, and then I have a sum from 1 to infinity. Right? And now I can exponentiate both sides. So taking exponential on both sides in that equation, that gives me okay. And because we have proved that these J and N's are just Hecke operator, equivalent Hecke operator applied on J and 1, I can simply write this as as this. Now, all we need to do is substitute the expression for this action of equivalent Hecke operators using this, and now do a few steps, and then we'll arrive at the infinite product identity. So let's see. Are there any questions, or I'll go on and do this calculation? Okay. How much time do I have? Okay. So in the last 2-3 minutes, let me just say what to do here. So once we substitute this definition here, then we will have a sum with the coefficients that I wrote down earlier. And then we need to invert the coefficients and write it in terms of those b tildes that I had written earlier. And doing a few steps, which are just algebraic manipulation, it's not that difficult. We will get the infinite product identity. Now, the same thing can be done with the BKO divisor formula, and that will give us the infinite product identity for the monster-Lie algebra. So that's another easy proof of the monster denominator identity. So yeah, thank you.
Yeah, any question?
Yeah.
What are the exact assumptions of your theorem?
So first assumption is that n is square free. So for that, that is required because I said there are extra terms here that we don't want. The other is that Jn1s as a function of h to c is holomorphic. So that will rule out a few capital N's. And for example, that is always true when x naught n is genus 0. And there are an infinite class of such n's for which this is true. This is also true when, for some primes, I believe. So for example, if x naught p is genus 1 for p prime, then also one can show that these functions are holomorphic. And then in those cases, this theorem applies. And there might be other values of n for which these are higher genus and still these are holomorphic. That might also happen. But at least for these two class, this definitely applies.
Any other question?
Yeah, that is known from, I think this paper. This is from 2017, I think. No, I think this is 21. So yeah, they proved this particular identity. And the extra term that comes up here is also given in that paper. That extra term vanishes when you take n square free.
Any other question? So let us